Now you can ask many questions. First of all, it's a bit counterintuitive. If you think about viruses in the context of regulatory cell, intuitively you would say, if you have a virus in the system, you would not want to activate or invigorate Tregs. And I'm bringing this up here. I don't show all the data because otherwise thousands of slides. Because indeed, what happens is that while the virus is in the system, the first week after infection, FOXP3 expression and Treg activity is down-modulated. This we can show experimentally very well. And you would intuitively say that makes sense. You get the flu, you don't want to have an augmented regulatory cell compartment. So for this we have good evidence, and we can discuss it later for those who want to see this. After the virus is out of the system, these Tregs emerge invigorated. So it's almost like a better re-establishment of homeostasis. It's quite interesting. And while this happens, these reinvigorated Tregs, I'll show you in a minute, also prevent very well the occurrence of type 1 diabetes. So when you look at these invigorated Tregs, what do we know about them? They make quite a bit more TGF-beta. They make a bit more IL-10. They also make more gamma interferon, which we don't know whether it's needed for protection. FOXP3 levels very similar, not increased after the virus infection. In vitro suppression, at least some of the suppression TGF-beta dependent. And if we do an in vivo transfection with TGF-beta of Tregs in vivo, it enhances their ability to suppress type 1 diabetes. So we have some good evidence that the augmented TGF-beta production is responsible for the increased protection. Question now, to close mechanistically this part of my talk, is this the only mechanism that viruses put in place to protect from diabetes? And the answer is no, and I'll show you the other mechanisms in just a minute. So what happens? It's quite intriguing. There are several mechanisms at work if you prevent diabetes with virus. So you can either do this with LCMV or you can do it with Coxsackie V. So if you just put in the Tregs itself, it doesn't have all of a protective effect. There's other mechanisms at work. What are the mechanisms and how do they work? We have delineated the role for PD-1 ligand and for TNF-alpha. And the way this works is that during an acute virus infection, you upregulate TNF-alpha and you upregulate PD-1 ligand on most T cells. This will happen with flu, Coxsackie V, many viruses. And these molecules, at the end of the day, are important to shut the antiviral response down. Okay? And if you do this in experimental models, I don't show you all the slides because we would just be flipping to 20, 30 slides. And some of this has anyways been published recently in JCI labs. What these molecules do is they eliminate not only the antiviral lymphocytes, but at the same time, they clean out a whole bunch of autoreactive cells because it's not an antigen-specific process. It's sort of a debulking process where the immune system gets overlaid with these inflammatory factors, just eliminates a lot of lymphocytes to return back to homeostasis. And this mechanism, for example, PD-1 ligand as well as TNF-alphas, they're instrumental. But what do they do actually? They delay the development of diabetes. They don't reduce the overall incidence. It's very interesting because you can draw, if you want so, I want so, and a parallel between immunotherapies that debulk, as Jeff Bluestone calls us, or delete lymphocytes. For example, anti-CD3, for example, ATG. Similar effect. What you get is a transient delay, and this is precisely what you see in humans when you give anti-CD3 or ATG. You get a delay because you lower the autoaggressive lymphocytes for a while, as long as you immunosuppress, maybe a bit longer, and then the disease re-emerges. So that's one mechanism. This PD-1 ligand was published JCI this year. TNF-alpha we published in JCI about 5 years ago, but Urs Christen was instrumentally involved in that. Second mechanism is the Tregs. Tregs do something different. As I talked just to you about, the Tregs become invigorated by the virus. And what happens is that the Tregs alone reduce the overall incidence, but in the mice where they're not enough, they don't delay anything. Similar to what you see after oral insulin tolerance. You always see this dichotomy, 50% prevention of diabetes, the rest develops diabetes just about as fast as the other ones. If you have both of these mechanisms together, and that really is what's happening in the curves that I showed you for the viral prevention. You get a delay in the prevention of diabetes. And it's incidentally interesting because those who were at the talk yesterday, I'm a great proposer of combination therapies. In combination therapies, when you do a systemically acting immunosuppressant and an agent that enhances Tregs, you want to achieve precisely this, a delay in an overall prevention of diabetes in this type of synergy. Now, for those of you who are interested in Toll receptors and the like, we have some good evidence that this process of viral prevention with the Tregs is TLR2 dependent. We don't know why it's TLR2 dependent, but we know that if we give a TLR2 antagonist, we completely lose this Treg effect completely. How it works, we don't know. The hypothesis, and we discussed this yesterday, that's most viable probably right now is that the viral inflammation leads to upregulation of all kinds of heat shock proteins, and among them are heat shock proteins that, as Iron Core and others showed, binds to TLR2, and in this way have a conditioning effect directly on Tregs and maybe dendritic cells, and they create a more regulatory environment. But we don't know that for a fact. We know very well it's TLR2 dependent. Maybe some other TLRs, but we haven't tested any other TLRs. So this is the viral story that we have so far, and that was the main topic of my talk today. We don't know whether other Tregs than these CD25 Tregs play a role in this. At least in the viral prevention, we have no strong evidence that IL-10 positive Tregs are induced by these viruses that are just an acute infection, are then eliminated from the system. So in terms of what this means for immunotherapy, and I will go fast on this because I spoke about this yesterday, but it's a good link and probably of some clinical interest. What are the perspectives today to prevent or treat type 1 diabetes? Given the complexity with the genes and the environment, it's probably difficult to follow the hypothesis that you can eliminate one virus or one gene and prevent the disease. It's a polygenetic disease, you have many infections. This is going to be complicated. Even if enteroviruses play a role in the process commonly, it's still going to be complicated to completely eliminate enterovirus infections in children, but maybe a possibility. Islet transplantation is right now difficult because it's become known that most of the islet grafts are lost after about 5 years through re-emergence of autoreactive aggressive T cells. So that evidence is pretty strong. This is not from our lab, but groups in Italy and so forth have studied this. So we remain with the issue of developing a good immunotherapy, ideally a prevention, and ideally an immunotherapy that has low enough side effects so you can give it to the population that's at risk at large for type 1 diabetes, among them many young children from families that are genetically predisposed. So the bar of not causing too much immunosuppression for this disease is set very, very high, and one has to keep this in mind. Therefore, my reasoning that you want to have a combination therapy. Ideally, what we want to do is we want to eliminate aggressive T cells and have long-term tolerance with Tregs, so we don't have to immunosuppress all the time. That's really what we have been working on for a long time. We go skip this because we don't have so much time.